Well, first of all, hi everyone there and virtually there. So it's a great pleasure for me to introduce our next speaker, Sibylle Schroll from University of Köln. Sibylle is a friend, colleague, co-author, and well, I'm very happy that she accepted to be speaker in this Encuentro Rioplatense. So, Sibylle, your turn.
Well, thank you very much for this really nice introduction, Andrea. It's a true pleasure to be here. Of course, I would have loved to be there physically. Hipólito beat me to it. Yes, and I have to apologize. I cannot give the talk in Spanish. Maybe I could just about master French, but Spanish is beyond me, unfortunately. Maybe one day. Okay, so this talk is on joint work with, on two papers really, three actually. One is with Ed Green and Lutz Hille, which is on varieties of algebras, and one is on joint work in progress with Ed Green and Eduardo Marcus. And basically, the idea underlying this is to use non-commutative Gröbner bases to construct varieties. So anybody who's done any commutative algebra will be quite familiar with Gröbner basis theory. That's very useful for many different things. But I think less people know that there's a non-commutative analog of Gröbner basis theory. And this exists not only for non-commutative algebra, but there exists a version for modules where then instead of in some sense being a two-sided theory, it's a one-sided theory, depending on whether we deal with left or right modules. Okay, and we want to use these Gröbner bases to construct affine algebraic varieties. And there are two different types of varieties. One are varieties where the points correspond to algebras, and the other one are varieties where the points correspond to modules. And I think the construction for the algebras is maybe slightly easier. So I thought I would start with that and first give you an overview of the idea, which is on that first slide. I'll go through it in a moment, and then tell you what this gives us, and then show you how the varieties for algebras are constructed, and then move on to the modules. Okay, so we start with these algebra varieties. So the idea, as I said, is to use non-commutative Gröbner basis theory, and I will define what a Gröbner basis is in a moment. And from that, we want to construct a affine algebraic variety in such a way that every point in this variety V we construct is an algebra of the form KQ over I. And I'm not sure if everybody here is familiar with quiver and relations. So I thought I would quickly in this margin here recall what a quiver is. So a quiver Q is simply a finite oriented graph. So it can have parallel arrows. So maybe it will look like that. It might also have a loop, and then maybe it looks like that. So let me label everything A, B, C, D, and E. And from a quiver, if we have a field K, so if K is a field, we can construct a path algebra, KQ. Okay, so we know that a path, an algebra in general, is a vector space on which we define a multiplication. So and a vector space, of course, is specified by its basis, or by one of its bases. And what is the basis here? So the basis is given by all possible paths in the quiver. So at every vertex, which I didn't draw, out of 4 vertices, we have a stationary path, so a path that goes nowhere. Every arrow is a path. And then we have paths of length 2, for example, this or this are paths of length 2, and so on. And this gives you a basis of the path algebra. And how is the multiplication defined? Well, we define the multiplication on the basis elements. And for example, if we have the path B and the path C, then we can form the product BC, which is simply given by the concatenation of the path. But if we had the product CB, that means we first do C and then we do B. Well, they do not concatenate, so that product would be 0. So you see also that this is not a commutative algebra. Okay, what else can we see? Well, of course, and then we extend the multiplication linearly to the whole of the path algebra, or of the whole of the vector space KQ. And then since we have this loop, well, we can do it once, we can do it twice, and we can keep on going. So this will be an infinite dimensional algebra. Okay, and once we are given an algebra, of course, there's many sort of choosing ideals or two-sided ideals inside that algebra allows us to construct many other algebras. So if we have I, a two-sided ideal, then, for example, it could be generated by the path AC minus DE, and then maybe we want the algebra to be finite dimensional, so we choose some power of the loop to be in the ideal, and then we get the quotient algebra KQ over I. And why in these varieties that I construct do I restrict myself to this? Well, in some sense, it's, if you want to study algebras, it's enough to look at that. And why is that? Well, if your field K is algebraically closed, then there's a theorem that says that any finite dimensional algebra is Morita equivalent, which means has the same representation theory to an algebra of the form KQ over I for some finite quiver Q and an ideal I. Okay, so this is why, in some sense, because I'm a representation theorist, I find it sufficient to investigate algebras of this form. So to go back to our story, we start with the non-commutative Gröbner basis theory, and then we construct a variety, but in secret, what we start with in some sense is a path algebra of a quiver, and then we construct a variety where every point in the variety is another path algebra of a quiver. And the other important feature of these varieties is that they have a distinguished point. And this distinguished point in the variety corresponds to something called a monomial algebra. And what is a monomial algebra? Well, if you make the analogy with polynomial algebra, so if you have an algebra that's, well, let's say a polynomial algebra in one variable kx, then of course you can, any polynomial will give you an ideal, and you can build the quotient, but there's special ideals, and that are those that are given by monomials. And in that case, it just will be algebras of the form kx over n as opposed to kx over some polynomial f of x. And of course, here we see that this algebra is much easier to study than this algebra here. And if we have a path algebra given by quiver and relations, then what does it mean to be monomial? So that means our ideal is generated just by path. So here an example of a monomial ideal would be this. So instead of having a relation like this or a linear combination of paths, the ideal is generated by monomials. And why is this good? Well, it turns out that monomial algebras, just as the algebra kx over x to the power of n, are much, much easier to study. And we know lots of things about monomial algebras that we don't know in general for finite dimensional algebras. Okay, so this is the ideal. And before I tell you how these varieties are constructed, let me tell you what we know about them. Well, okay, so our algebras might or might not be finite dimensional. But suppose we have a variety, and suppose that an algebra in the variety is finite dimensional. Well, then they're all finite dimensional because all the dimensions of all the algebras in the variety are equal, and therefore they're equal to the dimension of the distinguished point, the monomial algebra. Okay, what else? So all the algebras, so if A is an algebra of this form inside one of our varieties, have the same, what is called Carton matrix. So what is the Carton matrix? The Carton matrix is, in some sense, an important quantity that, associated to a finite dimensional algebra. Namely, it records the dimension of the homomorphism spaces between the projective indecomposables. Okay, that's a big thing, maybe if you're not familiar with this, or in another word, it's such that if our vertices are given by 1 through n, so if these are the vertices of our quiver Q for our algebra, then the ijth entry of the Carton matrix is given by all the path from the vertex I to the vertex j in the algebra kq over I. Okay, so somehow it records, in some sense, the path in the algebra. Okay, and it turns out that inside one of our varieties, all the Carton matrices are equal, and in particular, they're equal to the Carton matrix of this monomial algebra. Okay, then another important invariant for a finite dimensional algebra is governed by that of the monomial algebra inside the variety, and that's that of the global dimension. So what is the global dimension? So the global dimension is the supremum of the projective dimensions of all the finite dimensional modules over the algebra. So if you want to do homological algebra, then you always have to sort of construct projective resolutions. And these projective resolutions, they can stop and eventually be 0, or they can continue on forever, in which case, forever, okay. And the length, in some sense, of these non-zero terms is the global dimension. So it's finite if eventually all projective resolutions are 0, and otherwise it's infinite. And if, for example, you're familiar with group algebras, then you know that they're symmetric algebras, and they are always of infinite global dimension. So there, the global dimension would be infinite. But let's suppose that the global dimension of the monomial algebra is finite, then it bounds the global dimension of any algebra in the variety. Okay, and this allows us to show that if the global dimension of an algebra is, of the monomial algebra is finite, then something called the Carton determinant conjecture holds for any algebra in the variety. Okay, so what is that Carton determinant conjecture? Well, in, I think, 1969, Eilenberg showed the following, that suppose we have an algebra that is of finite global dimension. Okay, so suppose that the global dimension of our algebra is finite. Then this implies that the determinant of the Carton matrix of that algebra is equal to plus or minus 1. So that's what he showed. And then very soon thereafter, or maybe he himself conjectured that this should actually be plus 1. Okay, but this is an open conjecture, so we don't know. And I mean, I find this quite remarkable, right? I mean, how difficult can it be? We already know it's plus or minus 1. So all we need to know now is that it's plus 1, but it's open. However, we know that the Carton determinant conjecture holds for certain classes of algebras. And one class of algebra where we know that it holds is that the class of monomial algebras. That's a result by Wilson. And so then that means if the global dimension of the monomial algebra is finite, then we know that the Carton determinant conjecture holds for the associated Carton matrix. So the determinant is +1. But since all algebra in a variety have the same Carton matrix, we know that the conjecture holds for any algebra in the variety. Okay, so unfortunately, this is not enough to show the Carton determinant conjecture in general, but I guess it extends it to a larger class of algebras than we knew before. Okay, what is another property that we know holds for these varieties? Well, if the monomial algebra happens to be what is called causal or generalized causal, which I denote by D causal, then all the algebras in the variety will be causal. And similarly, if we know that the monomial algebra is something called quasi-hereditary, for example, category O, or any Schur algebra or Q-Schur algebra is quasi-hereditary. So somehow these are algebras that naturally occur, but it's not an easy thing to determine given an algebra. You don't necessarily easily see whether the algebra is quasi-hereditary or not, because the definition is a little bit involved, but it is quite easy for monomial algebra to determine. And if we know that the monomial algebra is quasi-hereditary, then all algebras in a variety are quasi-hereditary. And the reason that it's easy to determine for monomial algebras is actually with Ed Green, if you have an algebra, we showed that if you have an algebra that is monomial and of the form KQ/I, then there's a very combinatorial criterion where you just look at the quiver and your relations and you pick out vertices. And if you can do it in a certain order, then the algebra is quasi-hereditary. If this is not possible, then it's not. And if I have time, I'll show you exactly how that works in an example. Okay, but now let me tell you how these varieties are constructed. So we start with an algebra given by quiver and relations. And in order to sort of, in some sense, fix the quiver, we assume that the ideal is inside the ideal generated by the square of the error ideal. Okay, and then we denote by B the basis of finite path in Q. So this is a basis for KQ. And in order to do Gröbner basis theory, we always need an order. So we choose some well order on that set B. So well order means that any subset has a minimal element, and we want this order to be admissible, which means it should be compatible with multiplication. So if I have A less than B and I multiply both things with the same thing, then if both are non-zero, the same order should still hold. Okay, what is an example of an admissible order? For example, the length lexicographical order is admissible. So that means I order all my arrows. I say, so in our example here, suppose A is bigger than B, bigger than C, and so on. And then I first compare paths by number of arrows. And if they have the same number of, arrows, then I go lexicographically by this chosen order. Okay, so there's in some sense a choice involved, but I don't think that is so important here. Okay, but once we have chosen an order, then we can define the notion of a tip. Okay, so this is, in some sense, it picks out longest element, because what are our elements? So inside the path algebra, well, it's a vector space, and it has as basis the path. So everything is going to be a linear combination of path. So these are coefficients in the field. And since we have this order on these paths, then we pick out the longest or the greatest element in our order that has a non-zero coefficient, okay? And we call that the tip. So in some sense, maybe tip is not the best, but it's sort of the longest element in this linear combination of x, of x expressed in terms of as a linear combination of basis elements is the tip. Okay, we can then extend that to a subset. namely of the path algebra. So the tip of the subset is the set of tips of all the elements. Okay, and with that, we can say what a Gröbner basis is. Namely, okay, so a Gröbner basis is always for an ideal. So we have our ideal I in KQ, two-sided ideal, and then we take a subset of I, and this subset is a Gröbner basis for I with respect to our chosen order if, now, okay, so on the one hand side, we look at the tips of G. So we inside G, which sits inside, inside KQ, we pick out all the tips of the elements in G. And on the other hand, this also sits inside KQ. So every element in I is going to be a linear combination of elements in KQ, and we pick out the greatest ones there. And then we look at the two-sided ideal generated by the tips of G and compare it with the two-sided ideal generated by the tips of I. And if those two ideals are equal, then G is a Gröbner basis for I. Okay, so what I would like you to notice is that these are now only paths, right? Because while X is a linear combination of paths, the tip is just one of the paths in here. So these are both monomial ideals, and somehow I always think of them sort of sitting at the top there. And it's quite remarkable that if G is a Gröbner basis and we have this isomorphism of monomial ideals, actually the Gröbner basis generates the whole of the ideal. Okay, so you have the tip and all that hangs down, and you say something about the tips, and it shows you that everything in some sense is equal. Okay, and now we can also define what the associated monomial is. Namely, it's simply the algebra KQ over the two-sided ideal generated by the tips. And if we have a monomial ideal, then it always has a minimal generating set of paths, and this minimal generating set of paths is actually a Gröbner basis, and we denote it by T. Okay, then there's just another definition, namely of the non-tips. So if T is what is called the tips, because it is sort of the generating set of this tip ideal, then we call the non-tip everybody that's not a tip. So I take my basis and take away all the tips. Okay, and then there's something called a fundamental lemma, namely any choice of order gives us a vector space decomposition of the path algebra into the ideal plus the span of the set of the non-tips, okay? So this might seem like not a big deal, but really, I think everything that makes Gröbner basis theory tick is in this decomposition of the path algebra as a vector space in terms of the ideal and then the span of the non-tips. Okay, and what can we do with that? Well, it allows us to construct a particular Gröbner basis. And how does that go? Okay, so our tip set T here, the minimal generating set of the tip ideal, is of course a subset in KQ. So this means there's a unique element here and a unique element here, so unique GT in here and a unique NT in here, such that T is the sum of GT plus NT. Furthermore, because NT is an element in the span of these things, that means it's going to be a sum of n with some coefficient Ctn, and the indexing set is given by all n parallel to t and n less than t, and this comes from this equality, but I don't want to go into these details, it's not important. But what is important, that somehow we have these coefficients here. And now if we rewrite this by passing GT here and T here, then we get gt is equal to t minus nt, which I have written here as this linear combination. And if we do that for any t in t, we can build this set GCTN, and one can show that this is actually a Gröbner basis for I, and it's given by this direct sum decomposition, so it's special, and we call it the reduced Gröbner basis. Okay, so with this in mind, we can define a set. So remember, we start with our algebra KQ over I. We choose an admissible order on the set of paths in KQ. We have this generating set of the tip ideal of I. And then we can define the set VT, which is given by a bunch of vectors of scalars. They are in this n-fold product of K. And then we form for every vector here, we form this set here. So we have T minus, and then we have N going through the set of non-tips, and we take these CTN, which are given here. And we only take those vectors of scalars such that this set here is actually a Gröbner basis for the ideal generated by the set. So it's maybe a little bit much to do, but basically here is a subset of KQ. Okay, I shouldn't put, it's a subset, I'm sorry. So it's a subset of KQ. This subset of KQ is going to, we can generate a two-sided ideal with it. And then because this is a two-sided ideal in KQ. And since it's a two-sided ideal and we have chosen an order, it might not, it will have a Gröbner basis. And if this set itself is the Gröbner basis for the ideal it generates, then we take the associated set of scalars. Okay. Okay, and then what we show is that this is actually an affine algebraic variety. And I think the best way to sort of make this a little bit more concrete is probably with an example. So let's look at the following example. So we start with the quiver. So the quiver has 6 vertices, which I've labeled 1, 2, 3, 4, 5, and 6. And then it has these arrows A, B, C, D up to H. Now we choose an order, and I would like to work with the length lexicographical order. And for that, I order the arrows by stipulating that A is bigger than B and so on is bigger than H. Okay. Now I choose, because I want to start with KQ over I give myself a two-sided ideal, and the ideal I choose is the one that says, well, this path should be equal to this path, DE should be equal to FG, and then I have a bunch of monomial relations. Okay, and then I can build the associated monomial ideal, where I just pick out for every element in here the tip. So I don't take this, so I only have this. And then we see that this is automatically the minimal generating set T for the ideal generated by the tips of I. And that's, of course, a subset of B. And now I want to construct the associated variety VT. Okay, so here our set of non-tips is just going to be of dimension 2, because it's basically alpha beta, where I add a scalar here and here. And so potentially I could have all alpha beta in K2, but I want to just choose those such that this set here with now alpha and beta is a Gröbner basis for the ideal generated by the set. And how do I know whether this is a Gröbner basis or not? Well, there are some results in Gröbner basis theory that tell you if you can tip reduce this basically by t and to 0, then it's a Gröbner basis. So this gives us conditions, and this is done by reducing overlaps. And I don't really want to go into the details, but I overlap the relations with with our tip set here, and we see, for example, that this relation overlaps with BE here, and that gives us then alpha beta equal to 0. And so we see that here the variety corresponds to all alpha beta such that alpha beta is equal to 0. And then how do I see that the points in the variety correspond to algebras? Well, each alpha beta gives a unique G alpha beta, and this G alpha beta generates a unique two-sided ideal, and then the points are in bijection with the quotient of the path algebra by that two-sided ideal, and we only take those such that alpha beta is equal to 0. So these varieties are not necessarily the whole affine space, but they're also not always trivial. Okay. And what is particular for these algebra variety is that the associated monomial always is in the variety, namely it corresponds to the point 0, 0, because you see here that if you put 0 here and 0 here, then you have a monomial ideal. And if you compare with our definitions before, this gives the associated monomial, and it also always satisfies the equation. Okay, so this is the construction of the module varieties. And I had an example on the quasi-hereditariness here, but I might come back to it later if there's time. But instead, let me move on to the varieties of modules. Okay, so we now saw how to construct this, these algebra varieties, and all these algebras in the same variety have these good properties, and they're all induced by the associated monomial. And now we want to use a similar ideal to construct module varieties. And we did it really using this non-commutative Gröbner basis, and it's a project we've been working on for several years. I think it was not at all obvious to us what to do and where to go. And what is really remarkable is that I have recently talked about this at the Bristol conference for Bill Crawley-Bovey, and there's Sergei Motzkovoy in the audience. And we talked about it, and it turns out that these module varieties we construct are sub-varieties of non-commutative Hilbert schemes, which were defined by Markus Reinecke and Engel. So, and Johannes Engel, I think his name is. And anyway, so it's quite interesting that somehow this ad hoc construction we came up with turns out to be related to some varieties that the people have looked at. Okay, so what is the idea? Well, similarly, we use Gröbner basis theory, but now instead of using two-sided non-commutative Gröbner basis theory, we use right Gröbner basis theory. From that, we construct an affine algebraic variety in such a way that the points in the variety correspond to KQ mod I modules, and so that two modules in the variety share homological properties. Okay, well, we'll see that this is maybe a little bit harder to pass, but let's see what we know. Okay, so this part is joint work with Ed Green and Eduardo Marcus, and we show that if we construct such a variety, then all the modules in the variety have the same dimension, but not only the same dimension, but the same dimension vector. So somehow they have the same composition factors. And okay, and in order to tell you a little bit about the homological properties things share, I have to tell you something about a particular projective resolution. Namely, it's a projective resolution constructed by Green and Solberg. And this projective resolution is constructed using non-commutative Gröbner basis. And so it depends on an order. And so I've termed it order resolution. And it's very compatible with the construction of our varieties. The drawback of this order resolution, well, first the plus is algorithmic, so you can always construct it. The drawback is it's not necessarily minimal. And that, of course, is a problem. Okay, but we can define sort of the known homological quantities with regards to that particular resolution. So we define the O projective dimension. So if we have an order resolution, so this means we have M, then we construct a projective KQI module Q0 projecting onto M, and we have then another projective Q1M, Q2M, and so on. And this is going to be our order resolution. So all these are going to be projective KQI modules. And the O projective dimension of M is the sup of the n's such that Qnm is equal to 0. And I should have said Qn plus 1 is equal to 0. Okay, and then we can define the order finitistic dimension to be the supremum of the order projective dimension for all those modules that have finite order projective dimension. So if you just remove the O, then it's exactly the classical homological notions. Okay, with those definitions, we can show that if we have our variety, then all the modules in a variety have the same order projective dimension. And so we call it the order dimension of the variety. And of course, then the order dimension of the variety bounds or is an upper bound for the projective dimension of any module in the variety, because this projective dimension without the O is given by a minimal projective resolution, right? So this is always going to be bigger. And furthermore, we can show that the order finitistic dimension is always finite. And this means we get a reduction for the finitistic dimension conjecture. And this finitistic dimension conjecture says that without the O, this should always be finite. It's also an open conjecture in general. Yeah, I mean, it's known for some classes of algebra, but by no means all. And I think there's a lot of work on that conjecture. Anyway, so if we get the following reduction by our results here, it's enough to show that the supremum of the projective dimensions for all modules which are of finite projective dimension, but of infinite projective order dimension are finite. Okay, right. So this is somehow the homological properties we know for the module varieties, and then how are they constructed? Okay, so how do we do that? Okay, so we start with KQ over I in algebra, and we now pick some, let's assume finite dimensional, but it's not necessary, some module over that path algebra. Okay, then we take some projective KQ module surjecting onto M, and we know that over the path algebra, all projectives are a direct sum of vertex projectives. So they are a direct sum of projective modules of the form vertex times the path algebra. I'm considering right modules. Okay, then again, we need to choose an order. So we choose an admissible order on B, the basis of path of KQ. And then we fix some order on this indexing set of our direct sum. And this induces an order on the basis of path of our projective P. So I denote this projective of this basis of path of the projective P by B star. And where do I do Gröbner basis theory now? Well, the Gröbner basis theory is done, and I should say I choose not only the projective, but also as a surjection pi onto M. And the Gröbner basis is done on the kernel of that surjection. So we have the kernel of pi, which is some module Lm. And because this path algebra here is what is called hereditary, we know that any submodule of a projective module is again projective. So this is a very special circumstance. In general, if you have a finite dimensional algebra, this is not true. But if you have a hereditary algebra, which a path algebra is, then that is true. So we have this projective submodule of P, and we do the right Gröbner basis theory for this kernel here. Okay, so now what is a right Gröbner basis for that kernel? Well, it's a subset H star. So I put stars just so that we don't confuse it with the non-commutative two-sided Gröbner basis theory. So H star is a right Gröbner basis for the submodule M with regards or with respect to our chosen order, if the tip set of these things. So of course, in here, I mean, I have this basis here, I have a submodule, so everybody can be expressed in terms of the basis here, and then I can choose by our order for every element in the linear combination has a greatest element, and so I can define the tips. And if the right module generated by the tips in KQ the right module in KQ generated by the tips of H star is isomorphic to the right module generated by the tips of Lm itself, then this H star is a right Gröbner basis for Lm. Okay, and similarly to the above, again, a remark that if H star is a right Gröbner basis for Lm, then it generates the whole of the module. Okay, so now how are our varieties defined? Okay, so the varieties correspond to points, but also I said every point is a module. And how is that? Well, instead of writing our module M, which is P over L, I wrote it here as a submodule. So this is then some M prime. And okay, so then we take all submodules L of P such that the right ideal generated by the tips of L is isomorphic to the right ideal generated by the tips of KQ. But if I choose any random submodule of P, the quotient P over L is not necessarily a KQI module. So we want this to be a KQI module, and one can show that P over L is a KQI module if and only if Pi is included in L. So basically, I choose all such submodules that have the same tips as the module Lm that we started with, and such that P over L is a KQI module. This is the set I define, and then quite miraculously, this turns out to be an affine algebraic variety. And this is then by the sort of write-up of Sergei Motzkevoy, a subvariety of the non-commutative Hilbert scheme. Okay, but I think probably it's good to do an example. Okay, so here is an algebra. Oh, let me start like this. Okay, so this is our algebra. It has 8 vertices. And in the algebra, I choose an ideal, which is A, B, G, this path, so it's a monomial ideal. and I want to work with the length lexicographical order, so I just choose an ordering of the arrows. Okay, now I give myself a module M in KQ over I mod. And the module I choose is the following. So this is the module M. Maybe I should put it in a color so it's a bit easier to see. So here's my module M. And I give it by representation. So I guess one way of looking, if you have an algebra given by a path algebra modular relations, then there's an equivalence between the category of modules and the category of representations, where you replace each vertex of the algebra by a vector space, and where you replace each arrow by a linear map. And then somehow these linear maps have to satisfy the relation. So that means here, the composition of these linear maps should be 0, but of course, because we have the 0 map in there, it's automatically given. And then this gives you a representation which corresponds to a module over the path algebra. Okay, and then I choose a projective surjecting onto it, and I choose the minimal 1. So it's the projective in 1 plus 2 plus 3, which are all uniserial. So anyway, I've written it here, but if you're not familiar with it, just assume that there's this projective here. And then I calculate the kernel, which is given by the module 7, 8 plus 8. So there are 2 copies of 8. And then I can construct a right Gröbner basis for this module here, which is given by AB, CDG minus EFG. Okay, and then the tips in here, so the longest element according to our orders are simply AB, CDG. And here we can sort of now look at the set of submodules, and we can translate this condition here into Gröbner basis theory. And now what we want is we want to choose all those submodules of P such that P over the submodule is a KQI module. And how do we check that we get a KQI module is by checking that PI is in the module L, which is generated by that. And this is again done by reducing overlaps. And this is where somehow the equations appear, which allow us to show that we have indeed an affine algebraic variety. And I have written the reduction of the overlaps here. And then we see that here we pick all those Gröbner bases generating submodules of this projective module here that correspond to points x, y, z, such that xz minus y is equal to 0. Okay, so these are the module variety. And inside a module variety, there's going to be lots of modules that are isomorphic to each other. And it's not at all clear actually to us how things look, but by no means do we always get isomorphins, because I want to show you a second example, and that's a case of a hereditary algebra. So we have a very simple quiver. We have a quiver with 3 vertices and 3 arrows, so A, B, and C. Now relations. Inside this quiver, we pick a representation, or for this quiver, we pick a representation, M lambda, where we replace each vertex by the one-dimensional vector space. And then we replace A and B by the identity map. And then the map C is replaced by multiplication with a scalar lambda. Okay. And now we want to calculate the variety containing this module here. And that variety, so we basically calculate all the submodules here. that have the same tip set for their Gröbner basis as this. So we find, because we can't do any reductions because I is 0, that this is the whole of K. Okay, so we just get a line for our variety, but at the same time, we know that all these modules here are non-isomorphic. So if we have lambda different from lambda prime, then we know that m lambda is not isomorphic to m lambda prime. And so this means inside the variety, all the modules are distinct. So we have a line and each point is its own isomorphism class. So somehow it's really, I don't know, it's really interesting to me to see how different it is. And I think what makes it particularly interesting is that these are subvarieties of these non-commutative Hilbert schemes, which I think one understands probably even less than these module varieties. And I mean, here one can get some concrete examples and show how varied it is. Okay, so one last thing that I wanted to talk about is the distinguished point. So remember when we had the algebra, we had the distinguished point, which was given by a monomial algebra. And now we can do the similar thing here. We can look, or we can define something new called a monomial rod module. And this simply corresponds to choosing the point 0 or 0, 0, 0. Whenever we have a coefficient, we replace it by 0. And then this gives us this module. But it turns out that in this algebra, it's in the variety, in the previous one too, but we have examples where the associated monomial module is not a point in the variety. So somehow, while one can define this monomial module, it's not necessarily a point in the variety. However, it's the relations, because the Gröbner basis is so much easier because it's just given by monomials, these monomial modules have properties one can study more easily than you. So not much is known, but I believe one should be able to say a lot about them. And yeah, hopefully we will do that, or maybe somebody's interested in them. And then I would be very happy if somebody wanted to look at that. So thank you very much for listening.
Thank you, Sibylle. Questions or comments? So somebody...
Yeah, here's a question.
Yeah.
Hi, Sibylle.
Hi.
How are you? A couple of questions.
Okay.
The way you prove that your variety of algebras is a variety is, I guess, is you consider all possible reductions and the set of ideals which are, for whose the overlaps are resolved, form a closed set. So you
no, it's not like this. It's basically you take your set and you reduce, and you know that in order for it to Gröbner base it must be 0. So then that means that if you cannot reduce any further, which is the case here, then that implies that the coefficients must be 0, and that gives you a bunch of equations, and the zeros of the equations, of course, are then an affine algebraic variety.
So all the ideals in the variety are reduced in the same way?
Yes.
Ah, okay, that's nice. And,
yes.
So there is a generic resolution of all the overlaps.
Yes.
That's good. Okay, and then in this O, so in this thing about the finitistic dimension.
Ah, yes. Mm-hmm.
So you had this, you took the supremum of a smaller set. So this order infinite order projective dimension modules, they form a, so I don't remember how you construct the resolution, but I guess that if that has to be an intersection of open sets?
So there's no topology in the construction of the resolution.
But I mean, so in the order, when you do the construction, so you get to degree, say, n.
Mm-hmm.
So if the order dimension is infinite, that means that you have a kernel. No? So something is not zero, so you can change the coefficients in the module a bit, and it's still going to be non-zero. So the modules that have a non-zero kernel in degree something, it's going to be open, I guess. So this is an intersection of open sets. So my question is this set big or small?
I don't know.
Because if it is a countable intersection of open sets and non-empty, then it's really big in the variety.
Okay, so I mean, the problem with these order resolutions, although they're algorithmic, they're very, very difficult to understand and construct and work with. But I mean, intuitively, I would say that, yeah, I don't know. I mean, it seems to me that I don't know. I shouldn't say anything. I don't know.
And this thing about the Hilbert scheme?
Yes.
Do you know what subset you get? Because the Hilbert scheme is essentially the submodules of M with a fixed Carton matrix or something.
Yes. Which ones? It's some intersection, which is how you see that it is a sub-variety, but I don't remember which.
But it is closed.
Yes.
Oh, okay, thank you.
Okay, thank you. More questions there?
I was curious about, so you mentioned that you have several isomorphic modules in your variety, not always, but some of them, but you have an action of the general linear group in there, I think, that such that the orbits will be the isomorphism classes.
No. So there is an action of a group, but it's a subgroup of the automorphism group of your projective. So it's not the general linear group, because we consider KQI modules and not KQ modules.
Right.
And that's why we don't have an action of the general linear group, but there is a group action, and we can show that two modules in the same orbit are isomorphic, but we cannot show that two isomorphic modules are in the same orbit.
I see. And do you know what the orbits look like? Any idea of?
It's very abstract, because it's a subset. So it's a subset or subgroup of the automorphism group of the projective that sort of serves basically being in a variety, I suppose. So yeah, so
okay.
I mean, it's no, we can't really say much. We can, and as I said, we cannot even show that there's an equivalence between being in a more orbit and being isomorphic.
Then I think my question would more precisely be, what do you know anything about the group acting there? Is it?
No, we haven't really studied it. So yeah, so this is, as I said, it's work in progress, and it's sort of me talking about it is an invitation also for people to look at it, because I think there are more questions than answers at the moment. But I do think, I mean, for me, what makes it interesting is that it is sort of this sub-variety of this non-commutative Hilbert scheme. And so it's closely related, or it fits into sort of the bigger picture people are looking at, and it's not only an ad hoc construction.
Okay, thank you.
Thank you for your question. Who was that?
Pablo.
Oh, that was Pablo. Okay, I can't see, it's so small.
Hi, Sibylle. This is Hipólito. I have a question with respect to the varieties. I mean, if you start with the monomial algebra, the only thing that you get is a point. Am I right or not? Or not necessarily?
No, it's not true, because if you start with the monomial algebra, then you look at all paths parallel and is that right? Yes. So if you start, for example, with a gentle algebra, you get sort of non-gentle things in there.
Okay. So there is no there is no natural stratification in this variety. I mean, if you set certain equations equals to 0, this is not the variety of another algebra or something like this. No.
Yeah, I think it is, because in some sense, because basically, if you set certain, so yeah, we actually show that there are sub-varieties if you set certain parameters equal to something. So you can set them to 0, that always works, but even other values, as long as your equations are satisfied, and then you get sub-varieties which correspond to so you pick out a subset of algebras in there.
All right, so somehow the biggest variety starts with the monomial then, and then
no, I mean, you
the
can
smallest
start
one.
with any algebra, and it always, I mean, for the algebras, the variety always contains the associated monomial. So whether you start with the monomial or any other algebra in the variety, you get the same variety.
Okay. Okay, yeah. Okay. I can ask later. Yes.
Okay.
But
okay. More questions? No.
Hello, thanks for your talk. I have 2 more basic questions. Any small category gives rise to a quiver algebra, I guess. You take the arrows as generators and you quotient by all commutative diagrams.
Mm-hmm.
But I guess the quiver algebras are more because you can choose weird ideals to quotient with. So do you know, how can you characterize the algebras determined by categories among the ones that are quiver algebras in general?
Is that Mariano? What did he say?
I'm saying that you get all categories, no? So up to Morita equivalence, you just pick a generating set of arrows and you construct. It's like when you have a category and you add the endomorphism rings of all the objects and you get a finite dimensional algebra, you can go back and forth. Up to Morita equivalence, because you don't see the repeated isomorphic objects, because you only get the basic algebra in the algebra side.
Maybe maybe I understood wrong the question, but the question was that there were more algebras than the ones coming from these categories, right? I mean, I mean, I think there are, isn't it? But the question of the answer is no up to equivalence. Okay.
If you have if you have a linear finite category, then you can add the endomorphic, all the homes, and you get a finite dimensional algebra. And you can, if you have a finite dimensional algebra, you can split. You can find a complete set of idempotents, and you split it, and those are the objects of a category which has. So you can go back and forth.
Yeah. They're the same. Thanks. The second question is you mentioned this theorem by Eilenberg in the beginning.
Yeah.
I'm curious about how much can you prove if you only consider the class of algebras whose such that the determinant of the Carton matrix is 1. Only from that assumption, how good is it as a class of algebras?
I mean, for example, not clear because first of all, this is, I guess the conjecture is supposed to hold for all algebras, and it's known, for example, that is true for all monomial algebras. So I'm not quite sure I understand what you would like to do. Is just consider the class of algebra for which you know that the determinant of the Carton matrix is 1?
Yes.
And you mean what can one say for such algebras?
Yes.
I don't know. I'm not sure one can say actually all that much.
Thanks.
Interesting question. Is your question in some sense, why would one want to know?
I was wondering if it could serve as a good substitute for a class of algebras with finite dimension. But it depends on how much you can prove with only that assumption.
I mean, in general, I think that the Carton matrix is only considered for finite dimensional algebras. But I mean, I guess one could consider it for infinite dimension. Well, I don't know. Because, yeah, no, I mean, I think it makes a lot of sense for infinite dimensional algebras. Because then you probably sort of have entries in your matrix which are infinity.
Okay.
Maybe not always. You might have some path algebra in which okay, yeah, it might be. Sorry.
I mean, but what makes the algebra infinite? Either you have infinitely many arrows or vertices, or path of infinite length.
Right. Yeah, and then they would give, yeah, and this path needs to come at least for 2 vertices. I mean, okay, for 1 vertex, and then yeah, infinitely many times in 1 vertex. Yeah, and yeah, sorry. But are there infinite global dimension algebras with Carton matrix with the determinant equal to 1? It's like or -1 for that matter.
I don't know. I have never thought about it.
Because I don't think so. No.
I don't know. I mean, symmetric algebras have symmetric Carton matrices, but I don't know.
Okay.
Interesting questions.
Gastón, ¿hay alguien más?
No hay ninguna pregunta más.
Okay.
No further questions. Yeah.
There are no further questions there, and so thank you, Sibylle. Thank you a lot for the talk.
Thank you very much for listening and all the interesting questions. That's really fantastic for me.
Okay, thank you. And so the next talk is